Welcome to this beginner-level course on Docker and Kubernetes, an introduction into the world of DevOps, where our goal is to make the Docker and Kubernetes learning experience easy for everyone. Our focus throughout the course will be to, number 1, teach you the core concepts of Docker and Kubernetes. Number 2, use the Docker desktop application to understand the practical concepts of Docker and Kubernetes. Number 3, conduct practical, hands-on lab exercises that are designed in a way that covers all key concepts related to containerization and deployment. Number 4, test your newfound skills via 2 Capstone projects at the end of this course that will help you revise all of your concepts in one place and in one go. And finally, quizzes that are designed to test students' learning of key concepts. Meet our team who played a role in researching, designing, and creating this course. We have experience in practical implementation of different technologies and teaching technical courses at a university level. Our team members are specialized in areas relating to information technology, software engineering, data science, and more. We will have a total of 8 sections that are designed to help the student learn progressively. We will start from the basic introduction of the course and gradually move on to intermediate concepts covering Docker implementation, followed by the Kubernetes architecture and its best practices. By the end of these lessons, you will be able to deploy your own microservice applications using Docker and Kubernetes. Key concepts throughout the course are explained visually to enable our students grasp the technical concepts quickly and efficiently. The lab portion covers the key concepts of Docker and Kubernetes. A few examples are creating a Docker Hub account and installing the Docker desktop application to your PC, and also uploading images to remote repositories in Docker Hub. We will also look at the architecture of the Docker and Kubernetes engines and how they work under the hood. We will also be exploring writing configuration files for Docker and Kubernetes and how you can use these configuration files to containerize, deploy, and manage applications. Then, we will learn how to use Docker and Kubernetes using the command line interface, which is where you will be doing most of your work. We will be exploring different resources related to Kubernetes, including replica sets, volumes, CronJobs, and many more. Next, we will learn about some best practices relating to Docker, Kubernetes, and development in general. We will also be covering methods for high availability, in case your application shuts down for whatever reason. Finally, we will cover the Capstone projects for this course. The Capstone projects will include assignments related to the deployment and management of containers, as well as creating different resources in Kubernetes for the application as well. We look forward to having you join our course, and we promise that this course will help you build your foundational skills in learning Docker and Kubernetes. This course will help you make your resume stand out and demand a competitive salary in the marketplace. Hello everyone, welcome to this Docker and Kubernetes course. I'm glad you decided to join, and I hope this course will help you achieve your goals. To get started, let us have a look at the syllabus that we're going to be covering in this course. The Docker part of this course has been divided into 4 sections. The first section is the introduction, which will introduce you to Docker and its uses. We will also be explaining why Docker containers are a better alternative to VMs or virtual machines, and how to install Docker on your computer, whether you're using Windows, Mac OS, or Linux. The second section introduces you to the Docker architecture, where we will be introducing you to the Docker Engine, which is how Docker runs under the hood, Docker images, and also Docker containers. Finally, the third section will introduce you to practically implementing Docker concepts like containerizing and deploying a Docker application using Docker Hub, Docker security features, and much more. Have fun and best of luck learning. Hello everyone, welcome to this video. Today, we are going to be learning what Docker is and what it can be used for. Let's start with understanding what Docker is, and then we'll move on to discussing what it is used for. Let's get started. Docker is an open source platform that can be used to build, deploy, and manage parts of applications in containers. Deploying each part of an application in its own container is called the Microservice Architecture. The good thing about Docker is that it is available on all major operating systems like Windows, macOS, and Linux. Before containers, people used to use virtual machines to test applications. Virtual machines are much more secure than containers, but take a few minutes to deploy. The reason they are more secure is because its resources are completely isolated from the rest. Virtual machines need to be assigned temporary resources that are used while it is running. These resources are called guest resources. They are not accessible through the host machine while the virtual machine is running, which is what makes them so secure. Guest resources are assigned using a hypervisor. Along with the guest resources, a guest OS or a guest operating system also needs to be assigned so the virtual machine can communicate with the host computer. Examples of virtualization software include Oracle VM VirtualBox and VMware. Containers were created as a lighter solution to virtual machines. They can be deployed in seconds, but they aren't as secure as virtual machines. This is because they don't use guest resources or a separate guest OS. Instead, all the resources it uses are taken directly from the host OS, and only the individual application processes are isolated. Because containers don't need a guest OS or resources, they don't need a hypervisor either. When you compare virtual machines and containers side by side, they both are made for completely different situations. Virtual machines are used if you want maximum security for your application and don't care much about deployment speeds. Containers are used if you want maximum speed and find process isolation enough. It all comes down to what your application priorities are and what you're willing to sacrifice for something else. Although we compared virtual machines and containers quite thoroughly, we still haven't mentioned another advantage which containers have, called the Microservice Architecture. A monolithic architecture is an application that runs as a whole, meaning that all parts and processes of the application are bound together. If a part of the application goes down, the whole application goes down. If you want to update something, you have to bring down the whole application to do so. And finally, if you want to replicate your application for high availability, it would cost you double the amount of resources to do so. On the other hand, we have the microservice architecture. A microservice architecture keeps all the parts of the application separate, but they can still communicate with each other. If you want to update something, you could take that specific application part down, update it, and bring it back up without disturbing any other parts of the application. If you wanted to replicate a part of the application for high availability, you could easily do that while consuming as little resources as possible. Microservice architectures have many benefits, which is why a lot of companies prefer to use them instead of a monolithic architecture. Nothing comes without flaws, however, which is why we'll explore some disadvantages of the microservice architecture as well. For now, let us explore 3 benefits that the microservice architecture has to offer. The first benefit is that if a part of your application crashes, you can take that specific part down and repair it without disturbing any other part of the application. You can also put backups of each application part so that if a part goes down, you can just use its backup instead. Let's say my application's database went down, or I needed to add a new feature. While the component is down, the backup database component can work in its place instead until the original is back online. The second benefit is that if you want to add a new feature or upgrade to a new technology stack, you can upgrade that individual part of the application and you don't need to change anything else. Let's say I wanted to change my website frontend from a mean stack to a merge stack. I don't need to change any other part of the application to do this, and I can let my front-end components backup do all the work while the original is offline. Once the original is updated, I can bring it back online and update the backup with the new features that I added. This whole process didn't require me to touch the other components whatsoever. The last benefit we'll mention is the ability to scale any other part of the application at appropriate times as opposed to the whole application. Let's say I wanted to scale my database vertically because we're getting too many visitors on our website. I can easily allocate the extra resources required and don't even need to take it down. I can also decrease the number of resources once the traffic goes down. Now that I've discussed some advantages of the microservice architecture, let's discuss some disadvantages as well. The first disadvantage is the actual communication between the different parts of the application. When you have so many different parts, it gets very hard to manage, orchestrate, and network them together. The second disadvantage is the increased resource consumption when running a microservice architecture. Because there are so many different parts, the application eats up way more resources than it would normally do with a single part application. A single part application might take 16 gigabytes of RAM to run as a whole, but if it's A single part application might take 16 gigabytes of RAM to run as a whole, but if it's in a microservice architecture, each part would take at least 2 gigabytes. And if there are more than 8 parts, it would use up more RAM than using a single part application. This applies to all parts of the application, like the CPU and databases, not just the RAM. The final disadvantage we'll mention is debugging. This might seem to contradict what I said before about being able to upgrade and take down parts of the application with ease, but in reality, debugging is actually much more difficult than it looks. The reason for this is because each individual process has its own logs to look through. The more parts, the more logs. Hence, it's much harder to pinpoint the actual issue. I hope this video helped you understand what Docker is and why it is used. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be discussing what DevOps is and why it's better than keeping Dev and Ops separate. If you don't know what Dev or Ops is, we will be discussing that in the video as well. So let's start with the definitions first. Dev or development refers to the development of an application. This could be a web app, backend application, or cloud service. You can develop any application in many programming languages such as Python, JavaScript, and C++. Ops or operations refers to the operation and managing of an application, which includes deploying, orchestrating, networking, and any other things that are required to keep the application up and running. You can create and run operational scripts using scripting languages like Bash. You can also use networking software made for a specific task. In this case, you can use Docker and Kubernetes for creating and managing containers. Dev and Ops are managed completely separately from each other. The people working on operations don't know anything about how the application itself works, and the people working on development don't know anything about the management and networking of the application. This isn't the most ideal way to do things because it's very hard to debug, resolve issues, and improve the application overall if there are two separate teams doing their own thing and don't know much about each other's work. The solution? DevOps. DevOps is the practice of one team managing the development and operations of an application. This seems like a lot for one team to manage, which is why the operation side of things has been simplified tremendously using products like Docker and Kubernetes. This enables developers to focus on what's really important, which is developing, debugging, and improving applications. I hope this video helped you understand why DevOps is such an effective development practice in the IT world today and how Docker and Kubernetes fits into the picture. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we're going to be installing Docker Desktop on our Windows machine. First of all, navigate to this link, docs.docker.com/docker/windows/install. Here, you can see a button that says Download from Docker Hub. Click on it. This will take you to a new page. Over here, there's a button that says Get Docker. This will start installing the Docker Desktop installer. Keep in mind that this file is about 500 megabytes, so make sure you have sufficient storage. I have already installed the installer, so I'll skip this step. Next, let's go to our Downloads folder. Over here, you can see that there is a Docker desktop installer in my directory. Now, I will double click the exe file. This opens up a configuration menu. This menu contains two options. The first option is mandatory, while the second option is up to you. The reason the first option is mandatory is because this installs something called WSL2 on your computer. This enables you to run Linux commands and processes on your Windows machine. After you have selected your options, click on OK. Here, you can see that the installation has begun. Once it's finished, you have to restart your computer for Docker Desktop to work properly. As you can see here, the installation has now finished. Now, it's time to restart our computer. Here, you can see that I've just restarted my computer. In most cases, Docker Desktop runs automatically when the computer starts up. If it doesn't, just type Docker Desktop in the search bar and press enter. You might be getting an error that says WSL2 is not installed properly. It didn't happen in my case, but it might happen to you. If you get this error, then don't skip ahead. If you don't get this error, skip ahead to the Docker Desktop tutorial. To solve this issue, we need to navigate to this website, docs.microsoft.com/en/us/windows/install Over here, scroll down to step number 4. Click on this link over here, WSL2 Linux kernel update package for x64 machines. This will download a file over here. Let me click on it. This is the WSL2 installer. I already have it installed, so it installed automatically. Click on Finish to exit the setup wizard. Now that we've installed WSL2, let's restart our computer. If you try running Docker Desktop now, you will see that it is running perfectly. Now here, you usually have the option of taking a tutorial to see how Docker Desktop works. You can skip it if you like. Here, you can see that we are faced with a GUI. This GUI is where you can view our running, stopped, and paused containers. You will learn more about this later. That's it for this video. You now have Docker Desktop working properly on your Windows machine. Thank you so much for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we're going to be discussing what the Docker engine is and how it works under the hood. Let's get started. The Docker engine is the core software that runs and manages containers. It is designed to be modular with many swappable components. There are 3 main components which make up the Docker architecture. First of all, we have the client, which is us. Whenever we give Docker a command, we send that command to the Docker daemon, which is responsible for processing our request. This Docker daemon is contained inside the Docker host, which is the second component of our architecture. The Docker host is the main heavy lifter here, which is responsible for processing all of our requests for creating images and containers. It is also able to access what we call a registry, which brings us to our third component. The registry is where you can store all of your images in the cloud. The most common registry used is Docker Hub. We will learn how to use Docker Hub in a later video. For now, let's take 3 example commands and understand how each of them works in the Docker architecture. Let's start with the Docker build command. The Docker build command is responsible for creating an image. When you give this command to the client with your appropriate arguments, it processes this command and creates your image using the Docker file you supplied it with. If your image has dependencies that aren't available on your local computer, it may optionally contact the registry to pull those dependencies as well. Let's have a look at the Docker pull command next. The Docker pull command is responsible for pulling images from a remote repository like Docker Hub. First of all, you give your command to the Docker daemon for processing. Then, it has a look at the it has a look at the registry. To find the image that you requested for. In case you do not have permission to pull a specific image, this command won't work. Once it has found the image and confirmed you have the privileges to pull it, the image will be pulled onto your local computer. Finally, let's have a look at the Docker run command. The Docker run command is responsible for turning your image into a container. When you specify the command to the Docker daemon, it has a look at your local images to find the image that you specified. If that image is then not found, it will contact the repository to find the image there. And again, if you don't have the permission to access the image, the command won't work. But if you have permission and the image has been found, it will be pulled onto your local computer. Then, your image will be turned into a container. I hope this video helped you understand how the Docker engine works under the hood. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be discussing what Docker images are, how they are created, and how they are used to create Docker containers. Let's get started. You can think of an image like a container template or a stop container. They are used to contain your application in an easily portable manner. Once you have an image ready, you can run it and it will deploy as a Docker container. You can create your own image using a Docker file, which we will be discussing in later videos. You can also create dependencies for your image by adding other images into your Docker file. Images are also very lightweight because they are intended to be used only for a single application or service. Under the hood, images are made up of multiple layers that get stacked on top of each other to represent a single object. These individual layers are all read-only and cannot be modified. Each layer is also given a unique ID and a SHA-256 hash. In case you didn't know, a hash is the output of a hashing algorithm, which is used to encrypt data. And SHA-256 is one of the most popular hashing algorithms used today. You can assign a name and multiple tags to an image. Image tags are used to convey important information about a specific image version or variant. While image names are pretty self-explanatory, an image tag can be anything you like. The most common tag is latest. Using the latest tag on an image indicates that it is the most recent version of the image. This tag is also the default for an image if you don't mention a tag explicitly. Images can only be made for a specific architecture. This is why multi-architecture images were introduced. Multi-architecture images can run on any computer regardless of the architecture. Images can only be made for a specific architecture. This is why multi-architecture images were introduced. Multi-architecture images can run on any computer regardless of the architecture, whether it's ARM, Intel, or AMD. I hope this video helped you understand what images are and how they are used to create containers. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we're going to be discussing how Docker containers work in depth. Let's get started. We discussed in the previous video that images are like container templates. Well, a container is the runtime instance of an image, meaning that an image turns into a container when it is run. Docker containers can be in either of three states. The first is a running container, the second is a pause container, and the third is a stop container. A running container is an active container which is currently carrying out the processes that it's intended to. A pause container is an active container that has been stopped temporarily. Finally, a stop container is a container that is no longer being used and is not carrying out the process that it's intended to. We've discussed quite a lot about starting containers and managing them in three different states. Now, let's talk a little about stopping containers and the two different ways to do so. The first is sig-term, which lets the container finish up its processes and is then stopped. The second is sig-kill, which doesn't give the container any time to finish what it's doing and is stopped immediately. sigterm should only be used when you want to stop a container normally, while sigkill should only be used when you need to stop a container immediately, whether that's because of an error or an infinite loop inside the container. Finally, let's talk about restart policies. Restart policies are applied to each individual container. They're responsible for doing specific tasks in case a process inside the container fails. It's kind of like a self-healing method for containers. The first one is always, which means that whenever an error occurs inside the container, it will always be restarted. The second one is unless stopped, which means that if the user explicitly stops the container, it will restart the container, and in all other circumstances, it won't restart the container. The last one is on-failed, which means that if the container exits with an exit code of 0, it will restart the container. It will also restart the container if the daemon is restarted, but in all other circumstances, the container won't be restarted. I hope this video gave you a little more insight into how containers work. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be containerizing our first Docker application. What this means is that we are going to be creating the image that we will be deploying as a container in the next video. This is all going to be done from a pre-created web application which you can access in the description below. Now, let's get started. First of all, you have to download the folder. In this folder, let's have a look at the Docker file and what it contains. Let's open our Docker file using a text editor like Notepad++ if you're on Windows, TextEdit if you're on Mac OS, or Nano if you're on Linux. You can see that we have many lines here, so let's get started deciphering them one by one. The first line here is the from keyword. All Dockerfile lines start with the from keyword. All Docker files start with the from keyword. It is responsible for adding a base image, in this case Alpine, in the start directory as a dependency, which we can build on as we go further. Then we have the label keyword. The label keyword adds a key and a value which can both be decided by the file author that can be used to store metadata. In this case, our metadata is the creator of this file. We have a keyword called name, and its value inside quotation marks is my name. Then we have the workdir keyword. The workdir keyword sets your default working directory inside the container. It works by specifying a directory in the container to set as your current working directory. In this case, I commented out this line because all of the applications that we're going to be running are already executing in the root directory. Because they're being executed in the root directory, we don't need to specify any additional directories. Next, we have the run keyword. Anything that's written after the run keyword on the same line will be treated as a command that will run once the container has been deployed. In this case, we are installing and upgrading pip for Python. After that, we have the copy keyword. The copy keyword copies files from your local computer to the container just before the container is being deployed. It is a two-part command where the first part, in this case it's this part, is the location on your computer, and the second part, in this case this part, is the location on the container itself. Next, we have the expose keyword. The expose keyword is responsible for setting a network communication port for the application running inside the container, so it is not completely isolated and it can still access what it needs to work properly. In this case, we are exposing port number 5000 for the web server. Finally, we have the entry point and CMD keywords. The entry point keyword is used to decide the entry point of your application. This is the first program or process that runs when your computer is up and running. This is the first program/process that runs when your container is up and running. The arguments of the command are decided through another keyword specified after the entry point keyword, which is called CMD. Now, these are all the basic Dockerfile keywords that you'll need to know to start making Docker files. Now, let's turn the Docker file into an image that we can deploy as a container later on. This is called building an image and can be done with the docker image build command. Let's go to the terminal. This is the syntax for the command. Docker image build, the T flag, followed by the images tag. In this case, let's give it a name of Docker app, followed by the latest tag, and then a dot. Let's decipher this. First of all, the T flag is used to specify an image tag. We haven't discussed tags yet, but we will do in further videos. For now, all you need to understand is that the latest tag means that this is the latest version of the image currently being used. Then we have this dot, which basically says that the image is going to be built from the files in the current directory. As you can see, I am currently in the Flask app directory, so I don't need to specify a directory, hence I can just put a dot. Now if I click on enter, you can see that the image is now building, and now it has finished. If I have a look at my images using the docker image ls command, you can see I have an image called Docker app that has just been created. I hope this video helped you understand what a Docker file is and how it helps in deploying apps to Docker, as well as the basic keyword instructions used inside Docker files to make them work properly. In the next video, we'll be going over how to deploy our image as a running container. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be deploying the image that we created in the previous video. Let us get started right away. There are a range of commands that can be used for container management, like running, stopping, and restarting containers. The first command we'll explore is docker run. This command creates and starts your container from the image that you provided with. You can either deploy it in executable mode or detached mode. Detached mode means that it will run in the background constantly once it is deployed, and executable mode means that you will automatically be able to interact with the container once it is deployed. Exiting executable mode using Ctrl+C will kill the container. That is why, for now, we'll just create a detached container. Here's the syntax to create a detached container. Docker run, followed by the D flag, followed by the name flag, followed by the name of the container. We are calling it Docker app with a capital A, and then the image name, which is also Docker app but with a small a. So let's run this command. And as you can see, the container has now been run. After this, we can use this command over here, docker container ls, to output all of our running containers. So let's have a look at that as well. As you can see, this is our container. Each container is given a unique container ID. So this is the container's ID. Then we have the image that the container is using. In this case, it's the Docker app image. Then you have the current command that is executing. It's a Python command. Then you have when it was created 15 seconds ago. You have the last status. In this case, the container started up and running 13 seconds ago. Then you have the ports that is communicating with. Since this is a web server, it's communicating through port number 5000 using the TCP protocol. Finally, we have the name of the container itself, which is Docker app. Let's move on to some other commands. This right here is the docker pause command. The docker pause command is used to pause a running container. Here's the command: docker pause docker app, or in other words, the name of the container. Let's run this command. As you can see, it just outputted the container's name. This is normal for all of the commands that we're going to be viewing. Then let's output the container again. And as you can see, the status is currently paused, as you can see in brackets. Now let's unpause the container. Again, the command docker unpause is used to unpause a paused container. Pretty self-explanatory. So let's run this command: docker unpause name of the container docker app. If we output the container status, you can see that it is now running. Then we have the docker stop command, which completely stops a container. So if we execute this command over here, you can see that it's just going to output the same docker app or container name. You can see it's taking a while because we discussed about sig term and sig kill previously. So the docker stop command actually executes a sig term, and the docker kill command executes a sig kill. So the docker stop command takes a while to stop because sig term waits a few seconds for the container to finish its processes and then kills the container. So if we have a look at the output, the reason we have this A flag at the end over here is because this is now a stop container. If you do this by default, you can see that it won't show anything, and if we use the A flag, it will output all containers, including all of the paused and stopped containers. So you can see here that this container has recently exited exactly 32 seconds ago. Now we can start the container again using the docker start command instead of doing the whole docker run command again. That's also an option. So let's just use this command here: docker start docker app. And as you can see, it worked. Then if we output normally, you can see that it's up and running 3 seconds ago. Now let's have a look at the docker kill command. This will stop the container immediately because it's a sig kill and not sig term. So if we run this command here, you can see it outputs the name of the container, docker app. Then we have the output. Let's have a look at that as well. Again, we use the A output because this stops the container, and you can see it exited 7 seconds ago. Finally, we have the docker remove command. So once you've stopped a container, whether it is through docker kill or docker stop, you can remove the container itself completely, and you can do that using the docker remove command, or docker rm in this case, and then you specify the container's name. So let's give that a go as well. As you can see, here's the output, and then if we have a look at the normal output, you can see that nothing's outputted. And if we have a look at the output with the A flag as well, you can see that there's still nothing in the output either. Again, the reason for this is because we removed the container completely, so Docker doesn't know that it exists anymore. It's just completely removed, and Docker doesn't really care about it anymore. So this was an explanation of what Docker containers are and how you can deploy them. I hope this video helped you understand how to deploy an image as a container and how to manage that container in different ways as well. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today we are going to be setting up volumes to store persistent data in a container. Why do we need volumes in the first place? Well, if we have a container that works on and stores important information and it quits because of an internal error for some reason, all of that data that it was working on will be lost forever when the container is restarted. To prevent this, we can use volumes that store persistent data to ensure that when the container starts back up again, all of our data is safe and sound. Keep in mind that Docker volumes and Kubernetes volumes are very different from each other. Docker volumes work on individual containers, while Kubernetes volumes work on a group of containers together in a single pod. We'll learn what pods are later on in the course. For now, let's create our first Docker volume. Here's the command we'll use: docker volume create, and then the name of the volume. Let's call it my new volume. Let's run the command. you can use, here's the output, my new volume. As with the Docker commands previously, it just outputs the name of the volume. Now, let's have a look at the Docker volume ls command. This command basically just outputs all of the volumes you have available. As you can see here, we have a local volume that's called my new volume. Now, let's mount a container with the volume. We can do this by running a container and using the mount flag to mount a volume with the container. It's a two-part command. First of all, you have the mount flag and you have the source keyword. The source keyword basically indicates what volume the container is going to be attached to. Then we'll separate the two arguments with a comma, and then we have the second argument, which is target equals /vol. So /vol is the default directory that's created with every volume where you can store data. You can kind of think of it as a root directory, for example. Then you have the image name as normal. Let's execute this command. And as you can see, it outputted the hash, meaning that the Docker container is running perfectly. Now, let's explore the Docker volume prune command. This command basically deletes all of the volumes that are not mounted to a container. How are you going to test this? Well, let's create another volume, but we won't attach this one to a Docker container. So let's run this command. The volume is called volume to be deleted. If we have a look at the volume ls command, you can see that we now have two volumes right here. If we execute this command, docker volume prune, it should only delete the volume to be deleted volume and not the my new volume. Hope that's not too confusing because of the names. Let's execute the command. As you can see, it's stuck right now. The reason this is happening is because this command outputs something on the command line. So we need to have access to the command line to take yes or no for the command. Let's have a look at what I mean. If I go to the command prompt and I enter docker volume prune, you can see it gives me this warning. Warning, this will remove all local volumes that are not used by at least one container. Are you sure you want to continue? You can write a Y to say yes and a capital N to say no. What this says over here, not used by at least one container, indicates that yes, you can use a single volume with multiple containers. That's pretty interesting. Now, let's click on Y. And as you can see, deleted volumes, volume to be deleted, reclaimed space 0 bytes because we don't have any actual data inside the volume. So, the volume is now deleted. Let's have a look at our volumes now. And as you can see, this over here is still stuck. Once you have a stuck command inside Jupyter Notebook, you need to restart your kernel. I'll do that in a second. As you can see, I have reset my Jupyter Notebook and now I can run the commands properly. Let's have a look at my volumes. And as you can see, I only have the my new volume left. Finally, we have the docker volume remove command. This command is used to remove a volume normally, even if it's attached to a container. The problem with this command here is if I just try to run it normally, you can see it'll give an error from the daemon. And it basically means that you can't delete a volume if it's attached to a Docker container. So first of all, we're going to have to kill and remove the Docker container. Let's kill the Docker container first. Once this is done, let's remove it. Finally, let's remove the volume. And now, if you have a look at our available volumes, you will see that there are none left. I hope this video helped you understand what volumes are and how they are used to store persistent data in Docker. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be learning what Docker Hub is and why it is so useful. First of all, let's navigate to this website, hub.docker.com. Let's start by making an account. I already have one made, so I'll just log in directly. Keep in mind that when you create a Docker account and whenever you sign in, whether it's from the command line or the website, you cannot use your email to log in and you have to use your username at all times. Now, go to the repository section. This is your Docker Hub homepage. If you haven't figured it out already, Docker Hub is used to store images in the cloud. You will still have access to your images and can pull them from the registry at any time, whether it's using the website or the command line/terminal. You can also push images in the same manner. Docker Hub also allows you to upload multiple versions of an image to the registry if you like by giving it a different tag. Pushing and pulling from the website is pretty straightforward, so let's try to do the same using the command line/terminal instead. Let's use the same Alpine image we used in the previous videos. First of all, let's run the docker login command. As you can see, it automatically authenticated with the existing credentials from logging into the website and our Docker Hub account. Next, let's tag our image. The reason we need to do this is because when we need to upload an image to Docker Hub, we need to tag it properly. We can do this using the Docker tag account. We can do this using the Docker tag command. Here's the syntax: Docker tag, and then the image name. In this case, it's Alpine. The Docker Hub username, which is memelord. Our Docker Hub username, which is whatever it is. Then a slash. Then our image name, again Alpine. Then our colon. And then our tagging system, whether it's a v1, v2, or v3, or it's a default latest tag. I'll just go ahead and use that. As you can see, the image has now been tagged. So if we have a look at our existing images, Docker image ls, you will see that we have a memelord786/alpine image. Now we're going to be uploading this image to Docker Hub. We can do this using the docker pull command. We can do this using the docker push command. Docker push, and then the name of the image. Docker push, and then the name of the image, which is this right here. As you can see, this is currently uploading to the repository. Now it has been uploaded. Let's go to the website. And if I refresh, you can see that we now have the memelord786 Alpine image on our repository. Thank you for watching. As you can see, you now have a repository with the image name. Let's try pulling the image instead. We can do that using the docker pull command. Docker pull, and then the name of our image. If I have a look, Docker image ls, it didn't update anything because we already have the image in our local repository. But if we didn't, it would be added anyways. I hope this video helped you understand what Docker Hub is and why it plays an important role in the Docker lifecycle. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be reviewing everything that we covered in the Docker section of this course. Let's get started. The first thing we covered is what Docker is and some of its uses. As we discussed previously, Docker is a virtualization method utilizing containers that is faster when compared to virtual machines, but has worse security. Virtual machines also use what's known as a hypervisor, which is used to separate the guest resources from the host resources. Docker, on the other hand, doesn't use a hypervisor and uses the host resources directly. We also discussed how Docker enables us to create a microservice architecture for our applications, meaning that each application part is treated like a complete application and are kept separate from each other, but they are still networked together. We compared the microservice architecture with the monolithic architecture, concluding that the microservice architecture has a great many benefits over the monolithic architecture, but isn't completely without flaws, however. In the What is DevOps video, we separated the two parts of an application development team. The first is the dev team, or development team, and the second is the ops team, or the operations team. The dev team is responsible for developing the application, while the ops team is responsible for developing and managing the application. Having two teams working on the same application is pretty annoying, especially considering the fact that they don't have any idea about what each other are doing most of the time, so it's much harder to debug issues as well. The solution to this is DevOps. DevOps allows the dev team to use tools like Docker and Kubernetes to eliminate the need for an ops team completely. Then, we learned how to install Docker Desktop on our Windows, macOS, and Linux machines. While the Windows and macOS installations were pretty straightforward because of the availability of the Docker Desktop application, installing on Linux was quite a bit harder. Then, we learned about the internal workings of Docker, also known as the Docker Engine. The Docker Engine is made up of three main parts: the client, which is what we use to communicate our instructions to Docker; the Docker host, which is the workhorse of the Docker Engine, consisting of the Docker daemon, containers, and images; and finally, the remote registry, which isn't necessarily a part of the local Docker Engine, but is still a very important part in the overall Docker development environment. It is responsible for storing your local Docker images in the cloud, so it can be accessed at any time, anywhere. Then, we learned about Docker images. Docker images are how you wrap up an application part and later deploy it as a container. It is thought to be like a stock container. This image is prepared through the use of a Docker file, which consists of keywords like from, env, and cmd, to script the building of a Docker image itself. It is also responsible for piping the source code of your application into the image. Then, we learned how to deploy our Docker images as containers. This can be done by using the docker run command, which is a very important command in the Docker ecosystem. You can run a container in interactive mode or detached mode, and unless you need to do some manual configuration in the container at deployment time, you should use detached mode. You can also specify the port number where the container will be accessible to clients. In the next two videos, containerizing a Docker application and deploying a Docker application were practically implemented. In the next two videos, containerizing a Docker application and deploying a Docker application, we practically implemented what we discussed in the previous two videos, as well as getting hands-on experience with Dockerfiles and the Docker run command. Then, we learned how to use Docker Volumes to be able to store container data persistently. In case the container quits, that data will still be accessible to the container once it restarts. The first step is to create an unassigned Docker volume. Then, the Docker volume has to be assigned to the specific container. This can be done by mounting the volume to the container when running the docker run command. Once this is done, the volumes file will be accessible from the containers file, meaning that you can SSH into the container and easily store whatever data you want to that specific volume directory, which is mounted inside the container. You can even specify it in the Docker file itself. Then, we discuss some security features that Docker has to offer. The first and most obvious one is the built-in support that containers themselves offer. Containers themselves are derived from Linux containers, and Docker uses Linux in the backend, which is why we need to install WSL2 in the Docker installation video for Windows. Linux containers, formerly known as LXC, have a lot of security features built into them, like namespaces, control groups, and capabilities. As for security features that Docker themselves provide, the majority of them are available when working with swarms, one of them being join tokens. The Docker image registry, also known as Docker Hub, also has an interesting security feature that you can utilize. This is called Docker security scanning. Docker security scanning scans images on Docker Hub before you pull them in order to check for bugs and viruses hidden inside the image. It performs binary level scans and scans the software contained inside against a database, which contains a list of common bugs, viruses, and vulnerabilities. The reason this is necessary is because while the most important images on Docker Hub, like Alpine or NGINX, are verified, images made by third parties like you or me aren't verified, meaning that there is no guarantee about what they might contain. A detailed report is made available after the scan. The last video in the Docker section is the Docker Hub video. In that video, we learned about Docker Hub and what it can be used for. We also learned about how we can pull and push Docker images to the platform through the command line/terminal. I hope this video gave you an overview of everything that we covered in the previous video so far. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to the Kubernetes part of this course. I hope you learned a lot so far and are realizing the importance of DevOps along the way. To get started, let's have a look at the syllabus that we're going to be covering in the Kubernetes part of this course. The Kubernetes part of this course has been divided into 4 sections. The first section is the introduction, which will introduce you to Kubernetes and its uses. We will also be explaining you why Kubernetes is a must-have when working with Docker containers and how to install Kubernetes on your computer, whether you're using Windows, Mac OS, or Linux. The second section introduces you to the Kubernetes Engine and how everything works under the hood. The third section introduces you to Kubernetes resources, like pods, and how you can create your very own Kubernetes resources using YAML. It also introduces you to deleting resources and organizing pods using labels. We also have replica sets, which are a continuation to replication controllers. They both are very important for high availability in any microservice architecture. We also introduce you to resource management and how you can limit the amount of resources a Kubernetes resource uses. Finally, the fourth section will introduce you to some Kubernetes best practices. These include testing and development best practices, app management, and client request handling. Have fun and best of luck learning. Hello everyone, welcome to this video. Today, we are going to be learning what Kubernetes is and what its uses are. First of all, let's understand what Kubernetes actually is. Kubernetes is an open source platform that can be used to manage, orchestrate, and network containers together. Containers are grouped together in pods, which are the smallest computational units in Kubernetes. Using Kubernetes in your DevOps architecture has many benefits. Let's have a look at 3 benefits that Kubernetes has to offer. The first benefit is that it is compatible with multiple CSPs. These include AWS, Azure, GCP, and OCI. If you don't know what CSPs are, they are cloud service providers. They provide different services like CPU and GPU power, storage resources, application hosting, and much more. All of these services can be accessed remotely if you have an internet connection. Kubernetes and Docker can both be used with CSPs if you want to host your application in a microservice architecture. The second benefit is that Kubernetes provides a diverse range of storage options. We will cover Kubernetes Volumes later on in the course, but all you need to know now is that there are many different storage options you can take advantage of in Kubernetes. Some of these include empty dir, GCE persistent disk used with the GCP cloud provider, host path, and many more. The final benefit is that Kubernetes can work with any application that you wish to deploy. The reason for this is because Kubernetes doesn't care about the type of application that you want to host, whether it's a web application, database, or backend process. Kubernetes also doesn't care about the programming languages that you use either, which is a bonus if you want to update your application later on to a different framework, for example. Now that we have discussed some advantages about Kubernetes, let's discuss some disadvantages as well. The first disadvantage is that Kubernetes deployment can be very expensive. We discussed previously that hosting an application using a microservice architecture can be very expensive resource-wise. In case you decide to host your microservice application using a cloud service, you can still expect a pretty hefty price for your application. The second disadvantage is that Kubernetes is overkill for small applications. If you have an application made up of 3 services, the front end, the back end, and the database, you don't really need Kubernetes at all. Kubernetes is meant to be used for bigger microservice applications which have a lot of parts, as it is an orchestration/managing tool used for making it easier to manage complex microservice architectures. If your application only has a few parts, you can use Docker to deploy the application in containers, and that will work out just fine. The final disadvantage is that Kubernetes can be quite complex to use. While it is much better than managing Docker containers normally, it's still quite a hassle to manage everything properly, especially if you have a complex microservice architecture with multiple backups, parts, and interconnected networks. I hope this video helped you understand what Kubernetes is and what it is used for. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we're going to be installing Kubernetes on our Windows computer. First of all, navigate to your Docker desktop dashboard. Then, click on the settings icon in the top right. Then, have a look at the tabs over here. Go to the bottom tab which says Kubernetes. Then, click on the checkbox that says Enable Kubernetes. Then, click on Apply and Restart. Click on Install. You need an internet connection. And as you can see, Kubernetes is now installing. You can confirm that by having a look at the orange icon at the bottom left that is currently orange. As you can see, Kubernetes has now been successfully installed. You can confirm whether it's successfully installed or not by having a look at this icon in the bottom left. If it's green, it means that Kubernetes is now installed. I hope this video helped you understand how to install Kubernetes on your Windows computer. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we're going to be learning about how Kubernetes works under the hood. Let's get started. It is important to understand that the Kubernetes Engine, which is how Kubernetes works under the hood, is divided into 2 sections. The first section is called the control plane, or master node, and the second section is called the nodes, or worker nodes to be precise. The master node is what controls a Kubernetes cluster and makes it function. The worker nodes are machines that run your containerized applications. They're responsible for running, monitoring, and providing resources/services to your application. Now that we have a basic idea of the 2 sections that make up the Kubernetes engine, let's dive deeper into what components make up each section. Let's start with the master node. The first component we'll discuss is the etcd component. It is a distributed data store that persistently stores the configuration data of the cluster. In case the cluster goes down or is deactivated temporarily, Once it comes back online, the configuration will still be remembered by the Kubernetes engine. You can try this out for yourself as well. Navigate to your Docker desktop dashboard and click on Settings. Then, click on the Kubernetes section and uncheck the Enable Kubernetes checkbox. Then, click on Apply and Save Changes. Once Kubernetes is disabled, re-enable it by ticking the checkbox and saving changes again. You will notice that all of your Kubernetes resources are still available and nothing has changed. Next, we have the API server. The API server is how the client, which is you, and the other master node/control plane components communicate together. The API server also enables you to communicate with the different worker nodes on your cluster and their components as well. Then we have the scheduler. The scheduler schedules your apps. The scheduler schedules your apps, meaning that it assigns a worker node to each part of your application. This enables resource provisioning, management, and monitoring for each part of your application individually, in order to create an efficient microservice architecture for your application. Finally, we have the controller manager. The controller manager performs cluster-level functions like replicating components using replication controllers and replica sets, keeping track of all the worker nodes in a cluster, handling failures and crashes, etc. Now, let's move on to the worker node. The first component we'll discuss is the kubelet component. The kubelet is responsible for communicating with the API server on the master node/control plane and managing containers on its node. It directly communicates with the container runtime, which is also responsible for running your containers. It directly communicates with the container runtime, which is responsible for running your containers. There are actually many container runtimes that we can use, which we discussed in a previous video as well. The two most popular options are Docker and RKT. Finally, we have the kubeproxy or Kubernetes Service Proxy. The kubeproxy load balances. Finally, we have the kubeproxy or Kubernetes Service Proxy. The kubeproxy load balances network traffic between application components. It is pretty much like a Kubernetes service resource which assigns a static IP address which clients can use to communicate with multiple replicas of an application part, like the front end, for example. I hope this video helped you understand how Kubernetes works under the hood. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be exploring what pods are and why we use them. We will also be learning how to set up our own pods. Let's get started. As mentioned before in a previous video, pods are the smallest computational resource in Kubernetes. Pods do not do the computation themselves, but are just a managerial resource for the containers contained inside the pods. We use pods to group together containers that perform similar processes. Well, how about putting all of our processes into a single container? There are many downsides to this because containers are meant to contain individual processes rather than the whole application or a part of the application, like the backend. That will make it a monolithic architecture. This makes debugging and networking extremely difficult and defies the purpose of a microservice architecture in the first place, which is high availability. The more processes inside a container, the more processes are not available if the container goes offline. Cloning the containers for high availability isn't advisable either because it would mean cloning the whole application, and that would use up twice as many resources on the server, which isn't good. This is why pods have been designed to group together containers with similar or interconnected processes and enable networking between those containers as well. Let's say your backend application had 3 parts. You could group them together in a single pod. Now that you understand what pods are and why we use them, let us create our own pod. To create a pod, you need to create a file called a YAML file, YAML. This is similar to a Docker file, but it has a wide variety of uses as well and is used for describing how a pod is going to be created. We will explain the different parts of a YAML file in the next video, but for now, just copy and paste the code into a notepad like TextEdit for macOS, Notepad++ for Windows, and Nano for Linux. Change your Docker Hub username over here to your actual Docker Hub username. Now, save the file with the name example.yaml, and then let's create the pod. If I head over to my terminal, I can see here that here's my terminal. Keep in mind that the command that we're going to be using can be used for creating any other resource in Kubernetes and not just pods. You should get a message that says that the pod has been created successfully if it is created successfully. Here's the command: kubectl create the f flag followed by the name of the YAML file, example, and then the extension .yaml. And as you can see, the pod has now been created. If I have a look at kubectl get pods, you can see that the pod is running. You can also output the YAML of an existing pod by using this command: kubectl get po, short for pods, and then the pod name, example, and then the o flag followed by YAML. And here is the YAML of the pod. It's huge, but you can also output it in another way. Let's run the same command, except let's replace the YAML at the end with JSON, and then we can output the pod as a JSON file. I hope this video helped you understand what pods are and how to create them. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we're going to be learning the basics of YAML in Kubernetes. Before we start, it's important to mention that unlike Docker files, you won't be able to create any Kubernetes resource that you wish after this video. The reason for this is because there are many Kubernetes resources, and each has their own sections that you need to add or remove to create it. Without further ado, let's get started. YAML files are divided into a series of sections. Each section has a different purpose, and while each Kubernetes resource has its own new sections, there are a few general sections that each and all YAML files must have. The first is the API version section, which you can see over here. This specifies the version of the Kubernetes API that is to be used. The most common version is v1, which is also called version 1. The second is the kind section. The kind section specifies the type of Kubernetes resource that you are creating. In this case, we created a pod in the last video. The third is the metadata section. The metadata section contains the metadata of the Kubernetes resource, like its name and labels. The fourth and final section is the specs section, which contains the technical specifications of the Kubernetes resource that we are creating. The contents of this section are what differs the most from different Kubernetes resources. In this case, we are specifying the container that we will be creating with the pod, including its image, name, and ports. I hope this video gave you a general understanding of the four most important YAML sections used with all Kubernetes resources. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be learning how to delete resources in Kubernetes. Let's get started. First of all, let's start with learning how to delete pods. Deleting any resource in Kubernetes requires you to use this syntax: kubectl delete followed by the resource type followed by the resource name. Let's try deleting a pod. If you have a look at our running pods, kubectl get pods, we have the example pod. How can we delete this pod? We can do this using the same kubectl delete command. Kubectl delete followed by pod, which is the resource type, followed by the pod's name, example. Kubectl delete pod example. And as you can see, it says pod example deleted. And as you can see, my CMD is currently stuck. This is because it's sending a sig term to kill the pod. A sig term, as we discussed, means that the container takes up to 30 seconds to finish. And if the containers don't finish up in time, then a sig kill is sent to forcefully shut them down. And as you can see, the pod has now been deleted. I hope this video helped you understand how to delete resources in Kubernetes, including pods and other resources that we will cover in upcoming videos. Keep in mind that you can use the kubectl delete command with any resource that you would like to delete in Kubernetes. Thank you for watching, and I will see you in the next video. Hello everyone, welcome to this video. Today, we are going to be discussing what labels are and how they can be used to organize your Kubernetes resources. Let's get started. Labels can be used to organize pods and also other Kubernetes resources. It is an arbitrary key-value pair that you attach to a resource. You can use a label selector to filter out resources based on given labels. You can also add multiple labels if you want. To add a label in a resource's YAML file, you add a labels section in the metadata section. I'll use the same YAML file for the pod that we created in the first video of this section. I will add a labels section like this. Labels followed by the first I will add a label section like this. First of all, we have the heading labels, followed by the first key value pair, creation method, and then the value manual, and then another key value pair, env or environment, and then the value production. The creation method key value pair specifies the creation method of this pod, whether it was manually done or automatically done. The env key value pair specifies the environment of the pod, whether it's placed in production, development, testing, or any other namespace the company may be using. Again, you can create any key value pair that you like. We can just define the value as prod for short as well, which means production. Now, let's create the pod. We'll use the same command that we used before. kubectl create the f flag. Oh, forgot to save. There we go. kubectl create f and then the name of the YAML file, example, and then the extension .yaml. And as you can see, the pod has now been created. Now if we run the command kubectl get pods, we can see the pod is running, but where are the labels? We can't see any labels. We have to use the show labels flag with the kubectl get pods command. kubectl get pods show labels. And here we can see the two key value pairs that we have, creation method, manual, and environment production. Now let's modify the existing labels and add new labels to this pod. To add or overwrite a label, we will use the kubectl label command like this. kubectl label pods, the pod name, example, followed by the new key value pair. Let's call it app equals Flask, which is the type of web application that this container or pod is currently running. And now the pod has been labeled. If we run the command again, kubectl get pods show labels, we can see we have a new label, app equals Flask. Now that we have covered how to add and modify labels, let's learn. If we want to change the value of a pre-existing label, we can write the same key but a different value with the additional overwrite flag. If we do something like this, kubectl label pods example, and then we write the same key value pair again, it'll say that app or the key already has a value which is Flask and overwrite is false. What we can do instead is something like this, where we can replace this here with another value. Let's say app equals Python. And if we write the overwrite flag, the label has now been overwritten. So if we show this output again, kubectl get pods show labels, you can see that it has now been changed from app equals Flask to app equals Python. Now the benefit of doing this labeling is so that you can use label selectors. We use the normal kubectl get resource name, whatever it is, command to list the availability of specific resources, but by adding the L flag, we can also filter out the ones that have a specific label. That's what label selectors are. Something like this: kubectl get pods L followed by the key and the value. So the key, in this case, let's call it creation method equals automatic, and if we run this, it outputs nothing. The reason for that is because we don't have a key that is similar to this. Instead, if we write manual, it outputs the example pod. Let's try something else. You can optionally not use the value parameter if you want to display all the resources that have a specific key. Let's try doing this as well. kubectl get pods, the L flag, followed by the app keyword. And as you can see, it still displays the example pod. I hope this video helped you understand what labels are and how you can use them to filter out resources. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we're going to be learning what namespaces are and why they're used in Kubernetes. And no, they aren't like Linux namespaces that are used for process isolation. This is why we refer to them as Kubernetes namespaces from now on. Let's get started. Kubernetes namespaces are a way for creating non-overlapping groups for resources. They are useful when you're working with different teams or projects that all share the same Kubernetes cluster, but you still need to divide each project into a different group. By the way, Kubernetes clusters are a group of Kubernetes namespaces that are used to run an application. Companies usually just have one Kubernetes cluster and divide their processes and applications into different Kubernetes namespaces, but it is possible to create multi-cluster Kubernetes architectures. It isn't possible to do them with Minikube or with Docker Desktop, so we can't test it out, but using a cloud service like GCP or Google Cloud Platform is definitely a possibility. Kubernetes namespaces can also communicate with each other even though they are logically separated. Now that you know what Kubernetes namespaces are, let's create our own custom namespace. To do this, let's create a YAML file with this information inside it. First of all, we have the API version of Kubernetes, version 1. Then we have the kind of resource, namespace. Then we have our metadata, which includes the name of our new namespace. Let's just call it new namespace. To create a namespace, we have to change the kind of resource to namespace and give it a name. Next, let's create the namespace using the kubectl create command. Next, let's create the namespace using the kubectl create command. Then the file name. In this case, we saved it as namespace.yaml, so we'll just write that. And as you can see, my namespace has now been created. Once you have created a namespace, everything you do in your default namespace can be done in the other namespace by just adding the N flag. Here is an example of creating a pod in our new namespace using the YAML file we used last time. If I run this command, kubectl get pods, you can see for 16 minutes the example pod that we created in the last video has been running. But now, what if I want to create the same pod again in the different namespace? I can do this using this command, kubectl create the F flag followed by the YAML file example.yaml, but then the N flag followed by the namespace's name, new namespace. And as you can see, the pod has been created. If I run the command again, kubectl get pods, I can't actually see the new pod. I need to add the N flag at the end of this command as well. kubectl get pods N flag followed by the name of the namespace, new namespace. And here you can see that the pod has been initiated 23 seconds ago, which is what we just did. I hope this video helped you to understand what Kubernetes namespaces are and why they're used and how to create/manage one. I hope this video helped you understand what Kubernetes namespaces are and why they are used to create and manage. I hope this video helped you understand what Kubernetes namespaces are. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be discussing what replication controllers are and why they're such an important tool in Kubernetes for high availability. Let's get started. Replication controllers are a Kubernetes resource that ensures pods are always running. If a pod goes down, the replication controller replicates the pod with all the containers inside it, hence the name replication controller. Replication controllers also have the option to keep multiple replicas of the same pod running at all times. If the number of pods falls below a specific threshold, the replication controller creates more. A replication controller has three parts. The first part is the label selector. The label selector selects a pod to replicate with the specific label that is provided. The second part is the replica count. The replica count controls how many replicas of a pod must be running at all times. The third part is the pod template. The pod template controls what the replication controller bases off to create a new pod. Now that we know what a replication controller is and what its benefits are, let's learn how we can create our very own replication controller. To create your own replication controller, we need to create a YAML file for it. Copy and paste this code into a Notepad application like Notepad++ for Windows, TextEdit for macOS, and Nano for Linux. Let's have a look at what this YAML file does. First of all, we specify the kind of resource in the YAML file. Then, we specify the amount of replicas inside the YAML file as well. Now, let's create the replication controller using the kubectl create command. kubectl create the f flag followed by the YAML file's name. In this case, it's replication controller.yaml. And as you can see, the replication controller has been created. Once it's created, you can run the kubectl get pods command, and you can see that the three pods assigned to the replication controller are now running or being created. There's also a fun little command we can try called kubectl describe. Kubectl describe is used to describe the contents of any Kubernetes resource. This includes replication controllers. Here's an example. kubectl describe rc. rc is the short for replication controller, and then the replication controller's name, replication controller. And over here, it displays the YAML and settings of our replication controller. We can also use this other command called kubectl edit. The kubectl edit command is used to edit the YAML of any Kubernetes resource that you wish without creating a new instance. Here's the syntax. kubectl edit rc, and then the replication controller's name. And as you can see, it opens up the notepad that belongs to this replication controller, and I can edit it over here, save it, and then the effects will be changed over here. I hope this video helped you understand what replication controllers are and how they play an integral role in the Kubernetes environment by providing high availability to pods. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be learning about what replica sets are and why you should use them instead of replication controllers. Let's get started. The truth is that you don't really need replication controllers in the latest version of Kubernetes. Replica sets have been created as an alternative to replication controllers as they are much more effective. One of the main benefits of replica sets over replication controllers is the ability to be able to use more expressive label selectors. The only reason I showed you how to use replication controllers is 1. Because in some Kubernetes architectures that are outdated, replication controllers may still be used instead of replica sets. And 2. Because replica sets are harder to understand if you don't know how to use replication controllers in the first place. Let's have a look at the YAML file and commands that are used to create a replica set. First of all, let's create a new file in a Notepad application like Notepad++ in Windows, TextEdit in macOS, and Nano in Linux. Here's the YAML code that we're going to be using. There are two things to note here. First of all, the API version. The API version we are using here is a separate API used for specific resources called apps. Second, we have a match labels heading under selector. This match labels heading is there because we can use other options as well for more expressive label selecting. The match label selector acts just like a replication controller's normal selector. We'll use this for now, but later on we'll use the match expressions selector, which is more verbose. Let's save the file as replicaset.yaml and switch over to our command line/terminal window. To create a replica set, we'll be using the kubectl create command. kubectl create rs kubectl create the f flag and then replicaset.yaml. And as you can see, the replica set has been created. Now let's try looking at our pods. kubectl get pods, and as you can see, we have our 3 pods. They're either running or being created. If we have a look at our replica set, kubectl get rs, we can see that we have a replica set that is generating 3 pods and keeping them running all the time. Let's try label selecting. kubectl get pods, the L flag, and then let's try a key and a value. In our YAML file, we use the key app and the value flask. So let's try this. App equals flask. And as you can see, it selects all 3 pods. Let's try it with just the key. kubectl get pods, the L flag, and then just the key app. And again, it selects all 3 pods. This is working exactly like the replication controller. But now, let's delete the replica set and create another replica set with a more advanced label selector. We can delete the replica set using this command. kubectl delete rs and then the replica set name replica set. And now, let's modify our file by using the YAML code that we're going to be using instead. The difference here is that we are using the match expressions selector instead of the match label selector. The match expression selector is more verbose because you can select the operator you want to use for label selecting as well, which means that the key and the value entered. The match expression selector is more verbose because you can select the operator you want to use for label selecting as well. We use the in operator, but there are 3 other operators that you can use as well. The first is the not in operator, which means that the key and the value entered must not be included inside the label. The second is the exists operator, which means that the label should only have the key specified. The third is the does not exist operator, which means that the label should not include any labels with the specified key. The does not exist operator is the polar opposite of the exist operator, and the not in operator is the polar opposite of the in operator. Now, let's create our replica set again. kubectl create our kubectl create the f flag and then replica set.yaml. And as you can see, the replica set has been created again. Let's have a look. And we can see our 3 pods are either running or being created. Let's have a look at our replication set. Let's have a look at our replica set. And we can see that we have 3 pods here as well. Now what's the difference? Well, let's have a look at the kubectl label selector. kubectl get pods L and the same app equals flask. And you can see that it works just like the replication controller and the previous match labels selector. Let's try it with just the key. kubectl get pods app, and again it works in just the same way. This is because we use the in operator. If you use other operators, then we will get different outputs. Feel free to try it yourself. I hope this video helped you understand what replica sets are and why they're used instead of replication controllers. Thank you for watching, and I'll see you in the next. Hello everyone, welcome to this video. Today, we are going to be learning about cron jobs or chronicle jobs and how they're used to schedule specific tasks for specific times and dates. Let's get started. The whole purpose of a cron job is to be able to schedule a specific task to be automatically executed at its appointed time. Think of it like a YouTube premiere, where a creator can schedule exactly when a video is supposed to be released and let YouTube do the job automatically. This is one example of a cron job. In this example, we are going to be creating a pod using a cron job. To create a cron job, you need to create an empty file in a text editor like Notepad++ for Windows, TextEdit for macOS, and Nano for Linux. Here's the YAML code. Like the replica set, this resource is only accessible in a beta version of the Kubernetes API, as you can see over here. In the spec section, we have to specify the cron job timings inside a string, as so. In the spec section of the template section over here, we also have to specify the restart policy of our container. In this case, it is on failure. Now that we have our YAML file, let's create our cron job. Let's run the kubectl create command. Kubectl create the f flag and then the name of the file. In this case, it's cronjob.yaml. When you run the command, depending on your time, the cron job is either waiting to be executed or has executed for the first time. Let's have a look. kubectl get cron job. And as you can see, the cron job is scheduled to run every 0, 15, 30, and 45 minutes of every hour. What this actually means is that it runs every 15 minutes until eternity. We can also delete the cron job using the kubectl delete command. kubectl delete cron job. And as you can see, the cron job has now been deleted. To understand how we configured our cron job timings, let's have a look at the official Kubernetes documentation. As you can see, I am on the official Kubernetes documentation page. If I scroll down, this graph over here explains how cron jobs are configured in Kubernetes. There are a total of 5 sections in a cron job. As you can see, there are 5 asterisks to mark the 5 sections. The first section specifies the minutes from 0 to 59. The second specifies the hours from 0 to 23. The third specifies the day of the month from 1 to 31. And the fourth specifies the month itself from 1 to 12. And finally, the fifth specifies the day of the week, from 0 to 6. For the day of the week, Sunday can also be referred to as 7 on some machines, when you cancel out the 0. We can combine these sections to get the results that we want from a cron job. In this case, we specified the cron job to run every 15 minutes. The commas are used to specify. In this case, we specified the cron job to run every 15 minutes. As you can see over here, we have commas. The commas are used to specify multiple values in a single section. If we just wrote one value, like 0 for example, the cron job would run every hour at 0 minutes instead of every 15 minutes. The asterisks themselves, over here, mean that the job will run at every instance of that section. In this case, it's every hour, on every day of the month, on every month, on every day of the week. You can see how this can become complex very quickly, so make sure that you practice. I hope this video helped you understand what cron jobs are and why they play such a vital role in any Kubernetes deployment strategy. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be learning about services and how they can be used to expose IP addresses for clients to connect to. Let's get started. Previously, we discussed the high availability of pods and how you can create multiple replicas of a pod using replication controllers and replica sets. Well, if we make multiple copies of a pod and want to distribute the number of clients equally to each pod replica, How can we do that? This is done using services. Services have a static IP address which clients can connect to gain access to the application. When a client connects, the service acts like a load balancer which distributes the load equally to all the pods it is connected to. Let's see how we can create our own service and attach our 3 replicated pods to it. First of all, open an empty file in an application like Notepad++ for Windows, TextEdit for macOS, and Nano for Linux. This is the YAML code that we're going to be using. Here, we are specifying the port which is going to be receiving our client request, which is port 8080. The clients are then redirected to the target port, which is port 5000. The reason we are choosing port 5000 is because our Flask application is exposing port 5000 and that port is ultimately our client's destination. We will save this file as service.yaml. Let's create this replica set using the kubectl create command. kubectl create the f flag and then the name of the file service.yaml. And as you can see, the service has been created. If we use this command kubectl get svc, we can see that we just created a new service 8 seconds ago. This service over here, called Kubernetes, is a default service that is used with any Kubernetes cluster, so you don't need to worry about this. Now, let's delete our Kubernetes service. kubectl delete svc service. And as you can see, our service has been deleted. If you only want to port forward temporarily, instead of creating a service, you can use the kubectl port forward command. This is the syntax. kubectl port forward, the pod name, let's use our example pod, and then the initial port, which is 8080, where our clients are going to be connecting to, and then our forwarded port, which is port 5000. And as you can see, it is currently port forwarding from port 8080 to 5000. If I press Ctrl C, then the port forwarding is going to be stopped. I hope this video helped you understand what services are and how they can be used to load balance clients across multiple replicas of your pod. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be learning about Kubernetes volumes and how they can be used to share data across multiple containers in a pod. Let's get started. Unlike Docker volumes, Kubernetes volumes are capable of storing data belonging to all the containers inside a pod. It is important to note that there are many types of Kubernetes volumes in Kubernetes. It would be impossible to cover all of them here, so we are going to be using the most common one, which is the empty dir volume. The empty dir volume is just an empty volume used for storing data. Keep in mind that you cannot use kubectl get to view volumes in your cluster. This is because they are mounted to the specific pod and its containers that you specify in the YAML file. Hence, it's like an internal directory that is only accessible to the programs inside the pod's containers. To create an empty dir volume, open an empty file in a text editor like Notepad++ for Windows, TextEdit for macOS, or Nano for Linux. Then, copy this YAML code. First of all, in the containers header, we are specifying the containers that we want to deploy with the pod. Then, we are specifying the volume mount. The volume mount is where the container is mounted inside the volume. For both of our containers, we are using the root directory as the mount. Then, in the volume section, which is this last section over here, we are defining the volume to be used. In this case, we are creating one volume called volume. Creative, right? Let's save the file as volume.yaml. Now that we've defined our YAML file, let's deploy our pod and see what happens. kubectl create the f flag and then the name of the YAML file volume.yaml. And as you can see, the pod has been created. When we create the pod, it also automatically creates our volume called volume and mounts it to the containers inside the pod. Let's have a look. kubectl get pods. And as we can see, we have a pod called volume that is trying to create two containers over here. As you can see, there is a create container error. Nothing to be alarmed about. The only reason this is happening is because we are using the Alpine image as one of our containers. Because the Alpine image itself isn't a proper application, it automatically exits after its work is done. In this case, the only work that we assign to the container is to load the Alpine package. Hence, it automatically exits after a few seconds. I hope this video helped you understand what Kubernetes volumes are and how they are used to store data belonging to multiple pods in a container. I hope this video helped you understand what Kubernetes volumes are and how they are used to store data belonging to multiple containers in a pod. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we're going to be learning how to manage our pod computational resources in Kubernetes. Let's get started. There are two things that we can do to manage our pod computational resources. The first is to set resource requests, which is the minimum amount of CPU and memory, aka RAM, that our pod needs to run. You can think of this as the minimum resource threshold. The second is to set resource limits, which is the maximum amount of CPU and memory that our pod is allowed to use if needed. You can think of this as the maximum resource threshold. Now that you understand the two ways we can manage our pod computational resources, it's time to deploy our own pod with maximum and minimum resource thresholds. To create a pod with resource thresholds, open an empty file in a text editor like Notepad++ for Windows, TextEdit for macOS, and Nano for Linux. Then, copy this YAML code. The important thing to note here is this section over here, the resources section. We have two subsections inside called requests and limits. The request section specifies the minimum CPU and memory that should be provided to the pod at all times. In this case, the minimum resources assigned are 200 millicores for the CPU and 10 megabytes for the memory. The limits section specifies the maximum CPU and memory that should be given to the pod if needed. In this case, the maximum resources assigned are 1 core for the CPU and 20 megabytes for the memory. Let's save this file as resources.yaml and deploy our pod to see what happens. Let's deploy our pod using the kubectl create command. Kubectl create and then the pod's name, which is going to be. Let's deploy the pod using the kubectl create command and see what happens. Let's enter the kubectl create command. Kubectl create the f flag followed by the name of the file, which is resources.yaml. And as you can see, the pod has now been created. Let's have a look. Kubectl get pods. And as you can see, the pod is currently running. Let's have a deeper look into the YAML of the pod to see what's actually going on underneath. This can be done using the kubectl describe command. Here's the syntax. Kubectl describe pod, which is the resource name, and then the actual resource name, which is resources. And as you can see, here is the YAML that is currently being used. So if you have a look over here, you can see we have a limits and requests section. As you can see, the limits, 1 CPU core and 20 megabytes for the memory, and as the request, it's 200 millicores for the CPU and 10 megabytes for the memory. I hope this video helped you understand the two ways you can manage your pod's computational resources. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we're going to be doing something rather interesting. We're going to be exploring some software development principles, which are all acronyms that are commonly used in the IT field today. Let's get started. The first software development principle is YAGNI, which means you ain't gonna need it. This rule basically tells you to think of the core concepts that you may need to implement now and nothing else. Don't think about what you might need in the future, but instead keep it short and simple and leave everything else to actually do in the future. This enables you to focus on the important stuff and leave everything else for later. The second software development principle is dry, which means don't repeat yourself. It is the complete opposite of wet, which means write every time. You should implement the dry principle and not the wet principle, because the dry principle wants you to write code in a way where it is easily compatible with new features, while the wet principle wants you to rewrite the whole code base when you want to add a new feature, which isn't ideal at all. The third and final software development principle is KISS, which means keep it simple, stupid. This one's pretty self-explanatory, and all it means is to keep it simple. Don't implement complex, spooky algorithms for no real reason. Try to think of the simplest solution in your head and implement it the best you can. I hope this video helped you learn some of the most important software development principles out there, even though they have very weird names. But then again, that probably makes it much easier to remember. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we're going to be discussing some of the best practices for developing using Docker and Kubernetes. Let's get started. The first best practice you should start implementing is not using unnecessary image dependencies in Docker files. If you don't need it, there's absolutely no point you should use it. This is especially true with containers, because they need to be as light as possible in order to carry out their tasks quickly and efficiently. Even if you're confused whether you should use a dependency or not, it's better to try and find a way out of using it to be on the safe side. The second best practice is to use CMD and entry point keywords together, where the entry point keyword contains the main command to be run and the CMD keyword contains the arguments of that command to be run as well. If you go back to the Containerizing a Docker app video in section number 3, you will see that I use both CMD and entry point keywords together as well. The third best practice is to use spaces instead of tabs in YAML files. The reason for this is because YAML doesn't register sections properly if you use tabs. That's why, to be on the safe side, it's better to use spaces instead. The fourth and last best practice is that YAML is case sensitive, so other than entering names and labels, make sure everything else in the YAML file is lowercase. If you go back to the Basics of YAML video, you'll see that the first YAML file introduced in this course had spaces instead of tabs and was also in lowercase. I hope this video gave you some helpful tips on how you should be developing using Docker and Kubernetes. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, we are going to be reviewing everything that we covered in the Kubernetes section of this course. Let's get started. The first thing we covered is what Kubernetes is and some of its uses. As we discussed previously, Kubernetes is an orchestrating system responsible for managing multiple Docker containers together. Kubernetes consists of various tools called resources, which are used to help in the orchestration and networking of containers. Some of these resources include pods, services, and replica sets. There are many advantages of Kubernetes, including diverse storage options, cloud compatibility, and application compatibility. But there are also many disadvantages, including price, complexity, and the fact that it is unnecessary for small microservice architectures with only a few containers. Then, we learned how to install Kubernetes on our machine, whether it's using Windows, macOS, or Linux. The Windows and macOS installations were quite a bit easier, considering we had the Docker desktop application available. But the Linux installation was quite a bit trickier. Then, we learned about the Kubernetes architecture, specifically the Kubernetes Engine. The Kubernetes Engine is what runs under the hood. It consists of two parts, including a worker node and a master node/control plane. There can be multiple worker nodes, but only one master node in a Kubernetes cluster. The worker node consists of a kubelet, which communicates with the API server and updates its containers depending on its instructions. The instructions are sent to the container runtime, which takes these instructions and executes them. Finally, the kube proxy load balances network traffic between the application components in the microservice architecture. The master node consists of an etcd, which is a permanent data store for storing the configuration of the Kubernetes cluster, even if the Kubernetes cluster goes down. This etcd and all the other components on the master node and worker node communicate with the API server, which is responsible for sending everyone's messages across to everyone else. The scheduler assigns a worker node to each part of your application, which is important so that each application part can be monitored and managed appropriately according to the instructions of the master node. Finally, the cluster manager performs cluster-level functions like replicating components using replication controllers and replica sets, keeping track of all the worker nodes in a cluster, handling failures and crashes, etc. Then, we learned about the different resources in Kubernetes. Pods are responsible for grouping together like-minded containers so they can be controlled as a single object. Like-minded containers refers to containers that are made for the same function or application parts, like the backend containers or front-end containers. Then, we learned about how we can script different Kubernetes resources. This can be done through the use of a YAML file. YAML files are made up of sections, which contain keys and values. Based on the resource being created, sections are required to be added or deleted. Although some sections are necessary regardless of the type of resources you are creating, YAML files are made up of sections, which contain keys and values. Based on the resource being created, sections are required to be added or deleted, although some sections are necessary regardless of the type of resource that you are creating. Then, we learned about how we can delete Kubernetes resources if the need arises. It's simply done using the kubectl delete command, specifying the resource type and then the name of the resource. Then, we learned about how we can organize our pods using labels. Pods are the core resource in Kubernetes, but what if you have too many of them? How can you organize them into specific groups so that it's easier to manage? This can be done using labels. Labels are key-value pairs that are assigned to the metadata of a pod. You can specify the key and value and then find a specific pod with that key and value using a label selector. Label selectors are how you can find pods with specific labels. You can search by entering a key-value pair or just a key as well. Then, we learned about namespaces. Namespaces are a useful tool if you want to have multiple projects in the same Kubernetes cluster. Resources inside a namespace are completely isolated from resources in another namespace, which is useful so resources from separate projects don't get mixed. You can't exactly switch between different namespaces, but you can use the namespace flag to specify in which namespace a specific command is executed. Then, we learned about replication controllers. Replication controllers are used to make multiple replicas of a pod. This is useful in case of a pod exit, whether it's because of an internal error or something else. A new copy of the pod is immediately created when the old copy exits. You can also specify the minimum number of pod copies to be running at all times. If the number of copies falls below the threshold set, Kubernetes will automatically create new ones. Then, we learned about replica sets. Replica sets are exactly like replication controllers, but they have more advanced label selectors. Replica sets are a replacement to replication controllers, but replication controllers still may be used in older Kubernetes clusters, which is why it has still been included in this course. Then, we learned about CronJobs. CronJobs are timed jobs that execute at a specific time and date. They are configured using a specific cron job format, which is divided into 5 sections. You can think of a cron job like a YouTube premiere, where the video is released automatically by the system at the specific date and time specified by the creator. Then, we learned about services, which are responsible for using a static IP address that your clients can connect to. The service automatically load balances them to the different pods that are attached to your service. This can be useful if you have multiple replicas of the same service, like your backend service, for example, and want to load your This can be useful if you have multiple replicas of the same service, like your backend service, for example, and want to load balance your clients equally across all the replicas that you have. Then, we learned about Kubernetes volumes, which are not like Docker volumes because they are used for pods instead of individual containers. When you create a Kubernetes volume, you create it in the same YAML file belonging to the Kubernetes pod. This is usually done while you are creating the pod or by editing the YAML of the pod using the kubectl edit command. You have to specify the type of Kubernetes volume, whether it's empty dir, GCE persistent disk, or something else. You also have to specify the mount paths for each container inside the pod. Finally, we learned how we can manage our pod computational resources in Kubernetes. This is mainly done by setting CPU and RAM thresholds for the pod, also called limits, and setting the preferred amount of CPU and RAM that should be used for the pod, also called requests. CPU requests are specified as cores or millicores, and RAM requests are specified as megabytes. In the final section, we covered some best practices for developing and testing microservice architectures, including how to format Docker files and YAML files, as well as some general development rules like KISS and YAGNI. I hope this video gave you an overview of everything that we covered in the previous videos so far. Thank you for watching, and I'll see you in the next video. Hello everyone, welcome to this video. Today, I am presenting to you your final capstone project for all the Docker lessons that we have covered so far. This capstone will walk you through the entire process of deploying a Flask application, from creating the image for a pre-existing Flask application to deploying the image as a container. To complete this capstone, you have to have watched all the Docker videos we have covered so far and practice the practical labs as well. You must be used to creating Docker files, images, and containers to attempt this capstone. All of these concepts have been explained in sections 1 to 4. This capstone is a 4-step process. First of all, you have to create an image with the Flask application we use throughout the course inside it. Next, you have to upload that image to your Docker Hub account. Then, you have to create a container using the Flask application image that you created. But the catch is that you can't use the image from your local computer, and instead, the image has to be pulled from your Docker Hub account. Finally, once the container has been deployed, you have to delete the image locally from your computer. Once you have completed these 4 steps, congratulations! You have successfully passed this Docker capstone project. Keep in mind that solutions have been provided at the end of this PDF document. Please try the project yourself first before moving on to the solution. Next, let's move on to the Kubernetes capstone project. Hello everyone, welcome to this video. Today, I am presenting to you the final capstone project for all the Kubernetes lessons that we have covered so far. There are 4 things you need to do to pass this final project. First of all, you need to delete the Docker container that you created in the previous Docker capstone project. Next, you need to create a pod that contains the Flask application with a replica set attached to it. The replica set should have a replica count of 5. Then, you have to create a Kubernetes service that exposes a random IP address to the Flask application. Quick hint here, to find the IP address of the Flask application to be exposed, have a look at the YAML of the pod that we created. Finally, you need to change the YAML of the pod to keep 3 replica counts instead of 5. Once these steps are completed, you have officially passed the second final capstone project. Congratulations! Keep in mind that solutions have been provided at the end of this PDF document. Please try the project yourself first before moving on to the solution. I hope you enjoyed our journey throughout this course and learned about the wonderful world of DevOps and the 2 most important tools that make it a reality, aka Docker and Kubernetes. Consider checking out some of our other courses like our Git course for version control and our Python beginners course if you want to learn how to make Flask applications of your own. Thank you for joining me on this wonderful journey, and I wish you the best of luck in your future. Keep on learning.